All right. So, let's see here. I had a verse for this morning. This is Psalm 111:10. It says, "The fear of the Lord is the beginning of wisdom. A good understanding have all those who do his commandments. His praise endures forever." So I think it's good for us to remember where all of our wisdom and knowledge comes from, where we're all ultimately beholden to, right? Anyway, I'll begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class and this opportunity we have to meet and again study your creation. I just pray you to guide our steps today, Lord. In your name I pray, Lord Jesus. Amen. All right, I have a couple of, I think, just plain old math examples before I get to any applications today. So let's just do a couple. These two examples are somewhat preachy, so you'll see what message I'm preaching here after I get done with the second one. Example one. Oh well, that was a little bit off. Example one. So suppose you've got x plus 2y, and then you've got 2x minus y equals to 0 equals to 3. All right? So that's my example one. So let's solve this using the row reduction technique. Okay, so we write down the augmented coefficient matrix. 1, 2, 0, 2, minus 1, 3. Right? There's my augmented coefficient matrix. And now I'm going to do row reduction. All right, so first opening move here, row 2 minus 2 row 1. So 1, 2, 0 stays the same. And I get 0. Let's see here, 4 and 3. All right. And then I'm not going to quite do the algorithm which is in my notes. I'm just going to kind of modify it as suits my purpose here. And so what stands out to me here is that I could just do like, I could get rid of the 2 here by doing, let's say, row 1 minus 1/2 row 2. See, that would be nice. So I've got 1, 0, 0, 4, 3. All right. And what goes up here? Let's see here. 0 minus 1/2 of 3, which is minus 3/2. Any question? Yeah. I can make an arithmetic mistake, yeah.
First step, R2 minus 2, R1. Should the 4 not be a negative 5?
Oh, yeah, thanks. See, that, yeah, that's gonna, well, there it is. All right. So, it's important to do each step correctly. So if you have a comment about what I've done, do not wait, do not delay. Express your doubt as soon as you have it. This becomes all the more painful when I've gone like 5 more steps past that, right? So it's good that you did not delay, right? Not to mention, even if you're wrong, if you have that concern, probably somebody else does too. This class is for you, right? You can ask questions. All right, so, all right, well, in view of this pesky 5, I'm going to take a different tact. Oh, fine, I'll just do it. All right, so this is going to require a little bit of arithmetic on my part. So I need row 1 plus, I want to say 2/5 row 2. If I do that, 2/5 times minus 5 gives me minus 2. Minus 2 plus 2 is 0. That's what I want. I'm trying to eliminate that 0 there. Okay, so 1, 0, 0 minus 5, 3. I'm not doing anything to the second row. All right, so we got 3, rather 0 plus 2/5 of 3. What's 2/5 of 3? 6/5, right? Did I manage to do the arithmetic correctly this time? Let's see here. Are we good? Right. And then one more step here. I'm just going to take row 2 divided by -5. And that's going to get me to 1, 0, 6/5, and 0, 1, -3/5. All right? And what does that tell me? So this tells me that x is equal to 6/5 and y is equal to -3/5. In other words, 6/5 comma -3/5 is my solution. All right? Example 2. Suppose we're up against x plus 2y equals to 10, and 2x minus y equals to, oh, let's say 0. All right? So I'm going to use the row reduction technique again. So I start with my 1, 2, 2 minus 1, 10, 0. I'm going to do row 2 minus 2 row 1. That's going to give me 1, 2, 0, minus 5. Let's see here, what happens in the last column? 10 minus 20. Then I'm going to do row 1 plus 2/5 row 2. All right. That's going to give me, the first two columns are going to be 1, 0, 0, minus 5. Let's see here, row 1 plus 2/5. So what is 2/5 of minus 20? It is 40 over 5, which is minus 8. 10 minus 8 is 2. Right? Then what? To complete the story here, I get R2 divided by minus 5. I get 1, 0, 2, and 0, 1, 4. Being that I just made this example up, like off the top of my head, this is really cool. I got integer solutions. That's pretty cool. That doesn't have to happen, right, guys? So this is x equals to 2 and y equals to 4. In other words, the solution is 2, 4. So do you guys understand what just happened here in these two examples? What relates these two examples? Why did I go so much faster through the second one? Is that because you're awake more? Part of it.
All the steps are still the same.
All the steps are still the same because they both share the same coefficient matrix, right? They've just got different inhomogeneous terms. All right? Now, you could instead have done both of these examples at once, right? You could do both of these examples at once. In fact, you could do this. You could say that 1, 2, 2 minus 1 concatenated with 0, 3, 10, 0, right? You can do row operations. This will be row equivalent. Through this set of elementary row operations, well, not quite, but this set of row operations, this, then that. If you do those three to this, what you're going to get is 1, 0, 0, 1, 6/5, minus 3/5, 2, and 4. See, so once you understand this principle, if you're given multiple systems which share the same coefficient matrix, why not just combine your efforts and do it just once rather than doing it twice like I did in these examples, right? This is the remark I was making at the end of the last video, which I'm sure all of you have watched, right? Okay, good. So what's the deal with this? So this is a death to my partial credit, but I already did these steps twice, so it's probably okay, right? A little bit more here. So this, notationally, we introduced A and B. Now, A and B are not sacrosanct, but it's just my go-to if I'm not thinking. I'll call the coefficient matrix A, I'll call the inhomogeneous term B. That's just my default, notation. You could use others, we will. And then what we've calculated over here, right, this is the reduced row echelon form of the augmented coefficient matrix, right, which immediately reveals the solution. All right? Maybe is this clear? Can we go on? Let me work a problem with variables. We haven't done anything like that. And I think there's at least one in your homework with variables, and so I want to encourage you that you can do it. It's not that hard. You just got to follow the letters. So example 3, I'll keep it simple here. So something like, let's say x plus y equals to a, 2x minus y equals to b, and 3x plus y equals to c. All right, suppose I have these 3 equations and 2 unknowns, and I've got coefficients a, b, and c. I don't know what they are. My question is this: what condition do we need to put on a, b, and c in order that this system be consistent? All right? What does it take for this system? They're constants, yeah. So here, a, b, c constants with respect to x, y, z. Constants, what condition needed for system consistent? And of course, you guys could tell me, for instance, I know one choice that'll make it work. A, B, C, all 0. Right? If A, B, and C are all 0, this is a homogeneous system. Any homogeneous system automatically has the 0 solution, so yay, we're done. But that's not the question. The question is, like, what is the, what's all possible ways A, B, and C could conspire in order to make this a consistent system? All right, so let's do it. We'll use our go-to technique, which is row reduction. But now there are letters. So 1, 1a, 2, minus 1b, 3, 1c. All right, and I'm going to do row 2 minus 2 row 1, and I'm going to do row 3 minus 3 row 1 because that's just efficient, right? I can clear out the numbers below the pivot position 1 by making this strategic pair of row reductions, right? So the top row remains unaltered, but the next one, I get 0, and I get 0 here. Let's think through it. So like this minus 1. I get minus 1 minus 2, which is minus 3. And down here, I get 1 minus 3, which is minus 2. All right, I get B minus 2a, and I get C minus 3a. So you just, same song and dance, we just think symbolically. All right? Then what? Well, then at this point, what I would probably do just to make my, you can, like this kind of step, there's different ways to go here, but let me just make my thinking a little bit easier by dividing by minus 2. So this is like row 3 over minus 2. Nothing happens with the top 2 rows, they just stay the same. Of course, I guess I could do something, but let me just leave them unaltered. There we go. 0, 1. And so then we're going to get, 3 halves a minus c over 2, right? Okay, and then I can use that 1, right? I can use that 1 to clear out, come on, yowzers. I can use this 1 here to clear these guys out, right? I can subtract off those 2 using the following moves. Row 2 plus 3 row 3, and row 1 minus row 3. All right, so that's going to give me 1, 0, 0, 0, 0, 1. Nothing happens with the third one, so that's 3 halves A minus C over 2. And now I'm going to have to think about the last two things. The last two things is where the rubber meets the road, right? All right, so we've got row 2 plus 3 row 3. So maybe it helps to write this off to the side. My row 2 is B minus 2A, right? And I'm doing plus 3 times row 3, which in this case is 3 halves A minus C over 2, right? So that, let's see here. That's 9 halves minus 4 halves, which is 5 halves A. There's a single B, that's lonesome there. And how many C's do I got? Looks like a minus 3 halves C. All right, so that's that one. Now you could try to do it in your head, and it might go okay. I usually do. It sometimes goes okay. But since I already made a mistake today, I figure I'll show my work. Let's see here. So do this one. I need to do row 1 minus row 3. All right, so we've got A minus 3 halves A minus C over 2, right? That's what goes here. That would be minus 1 half A. Let's see here, plus C over 2, I think. Now, have I found, is this the reduced row echelon form of the coefficient matrix? Like what we're looking at right here. Is this RUF of the augmented coefficient matrix? I mean, its first column is E1. Its second column is E3, right? So does that, what is it? Is this the row reduced echelon form? It is not. Why not? Because the pivot columns have to be E1, E2, E3, and so forth. So for this, we'd be looking for E1 and E2, right? And, but you know, the thing is, do we need to calculate the reduced row echelon form in every single problem, whether or not we've been told? We do not, right? This is a tool. What is the purpose of the tool? The purpose of the tool is to see through problems which maybe are a little bit organizationally challenging, right? To like clearly see the solution. At this point, we can clearly see the solution, right? So like, for example, the first equation and the third equation, there's no problem there, right? What's the problem? What's challenging the consistency of this problem here, right? This guy right here. What's this mean as an equation, right? Remember, the row operations give us equivalent systems, right? Which have the same solution. So that middle equation, it tells us that 0 times x plus 0 times y is equal to 5 halves a plus b minus 3 halves c. Well, that's kind of hard to do unless there's only really one way to salvage that, which is what? We must have what? We must have that this must be 0, right? In order for this system to be consistent, we must have that that's 0. So the condition that we would want on a, b, and c here is that 5 halves a plus b minus 3 halves c is equal to 0. So there you go. That is the general condition which is needed in order for these 3 equations and 2 unknowns to be consistent. Graphically speaking, what's going on here is you've got, y is equal to a minus x. You've got y is equal to 2x minus b. You've got y is equal to c minus 3x, right? You got these 3 equations, right? And what we've just found is the condition that's needed for all 3 of those equations to actually meet at a point. all three of those lines to actually intersect at one single point. That doesn't usually happen for lines of unequal slope, right? Usually they'd make some sort of triangle where they miss each other. But not if we choose A, B, and C to so conspire. And one special case of that, which I saw from the outset, was just that they're all 0, right? Because that's something we can hang our hat on. Homogeneous systems are always consistent. All right. So any questions? That's my 2 cents for today. I'll go on to application stuff next, but if you guys have questions about the homework or something, we do have time today.
Sure.
Yeah.
So I was going through the homework yesterday,
Mm-hmm.
and I'm not sure if you said this, perhaps you did, and I missed it, but if you have a matrix in which
Mm-hmm.
the number of columns is greater than the number of rows.
A matrix in which the number of
It's a
columns.
hard question to visualize, so.
So a matrix in which the number of columns is greater than the number of rows. So like something like 1, 2, 3, 4, 5, and then 1, 1, 1, 1, 0, for instance.
Sure.
That one, yeah.
Then you're only able to make the first two columns pivot columns.
Possibly, but it could. But this could happen to you,
True. But let's say that doesn't happen, I guess.
or even this could happen to you.
What are the examples like that?
That could happen to you.
Yeah.
Although this is kind of annoying that I wasn't videoing it.
Oh.
Not your fault.
So, okay, like, I guess you're only able to make 2 of them in general. But
Yeah, up to 2.
Yeah.
Right. Now, of course, there could be this situation. I don't know why I'm doing 1, 2, 3, 4, 5. Like we could do with less. But you see, this is row equivalent to 1, 2, 3, 4, 5.
Yeah, true.
And that would be the reduced row echelon form of that. Well, your question?
I was just going to ask, do you want our answers in that format or is like a set of points?
Oh, well, you know, I think you could write x equals 6/5, y equals minus 3/5 and box them both. Or you could box the pair. Sometimes I'll ask for a solution set. But, okay, so solution set. Not great for these examples because it's kind of silly. There's just a single solution if there's one. This one, on the other hand, you know what happens? This is row equivalent to 0, 2, 3, 4, 5. Subtracting that one, 0, 0, minus 2, minus 3, minus 5. And then that is row equivalent. So here, that is row equivalent to 0, 1, 3/2, 2, 5/2, and 0, 0, minus 1, minus 3/2, minus 5/2, which is row equivalent to, ew. Whatever. Fine, I'll show my work. So like row 1 plus 3/2 row 2, 0, 1, 0, 0, and fine, 0 minus 1. All right, so I need to do, what's 3/2 of 3/2? 3/2 times 3/2 is 9 quarters. So I've got minus 9 quarters plus 2.
Minus 1/4.
Minus 1/4, thank you. And still minus 3/2. Got to think about this last one. Actually, let me fix it. Here.
Problem solved.
There you go. All right. Fix that. One more step. This example is pretty nefarious in terms of like the row reduction stuff. It's got some weird stuff going on. All right. Yes. So, yeah.
I was just going to say, so when we write the solution set, you're going to have like a free variable, is that what it's called?
Oh yes, there will be free variables. So like this one's especially weird. Let me just, but in order to make sense of the solution set, we have to actually like, I just wrote a matrix down. Like, so let it be understood that this was 2x2 plus 3x3 plus 4x4 equal to 0, and like 2x2 plus x3 plus x4 equals to 0, right? Yeah.
Shouldn't the bottom equation be equal to -5?
But
They should all be 0 then.
aw, man. All right, there, let me fix those. So sorry, guys. I worked to get that -5, and I undid my work by erasing that. So it is what it is, but it's okay. And why is it okay? Because row reduction goes column by column, right? So what stays in the last column, well, what's in the last column stays in the last column, right? And in particular, if it starts with 0, it stays 0. So that's cool, right, in terms of modifying board work. Sorry. I'll try not to do that too much. But OK, so great. That system of 2 equations and 4 unknowns, right, is the same as this one. But this one I can put in standard form. See, this says x2 is equal to 1/4 x4. And this says x3 is equal to -3/2 x4. All right? So what's the solution set here? So the solution set will be in terms of parameters. And the parameters will involve the non-pivot variables. What are the non-pivot variables here? Let me circle them. So like non-pivotal variables here, this guy and this guy, right? x1, x4. Those should appear as parameters in the solution set. See, because x2 and x3 depend on the non-pivotal variables, actually just x4. So they depend on x1 trivially. Really, x1 is just its own thing. So the solution set is x1, comma, 1/4 x4, comma, -3/2 x4, comma, x4, such that x1 and x4 are real numbers, because we keep it real in here. Now, if you're looking at the book or something, they might do some kind of thing like, well, I'm going to put an s here, and I'm going to put a t here, and I'm going to put a -3/2, and I'm going to put a t here, and I'm going to put a t here, and then I'm going to say s and t are real numbers. So yeah, and that's the same answer. But now you've sort of clouded the meaning of what the parameters are. So I actually prefer to use the coordinates as parameters because they reflect where they're coming from a little bit better. But this is the standard solution. So if I ask for the standard solution, this is what I'm talking about. Because are there other ways of writing the solution? Yes. And do I want to make the grader judge every one of your solutions that's written in a non-standard way if it's equivalent to the standard way? I do not. Therefore, I just say write the standard solution. So if you write a non-standard solution, which is also correct, it will be counted wrong. So I know it's kind of a jerk move, but you know, it is what it is. So sorry. But I've tried to grade the other in the past, like just, oh, I want to be generous. These students are just learning. Let me let them have all possible ways of writing the solution. No, no, it's bad. There are many, many ways to express the solution to this problem other than this. But this way is unique in its expression because it's attached to the row reduced echelon form of the augmented coefficient matrix, which itself is unique. So once you commit to writing the pivotal variables in terms of, you know, in terms of the parameters which correspond to the non-pivotal variables, that uniquely fixes the form of the solution set, which is a nice thing if you're trying to check your work with your like classmate or something, right? But all right, other questions? Yeah.
Is there any reason to include the 2 zeros in front of the matrix when you're doing the reduced echelon form?
Sure. This might be part of a larger story where x1 appears, and it just happens that x1 is not part of this problem. You know? I mean, x1 might like represent the number of good cats in the problem. So it's kind of a trivial variable. They're always 0, so it just rides along, something like that. Yeah, I don't know. But yes, it is kind of silly, right? In some sense, you're like, this isn't genuinely a problem of 4 variables. This is really a 3 variable problem, right? And if you're really lazy or wise, or maybe a little bit of both, do we need the last column for this example? No, right? Like a homogeneous system, you can lop off the inhomogeneous term and work it out, right? Because what happens to the last column is just 0. But I'd say for you guys right now, it's probably a better practice just to write the zeros and let them ride along so that you don't get confused, right? Like the zeros are helping us remember that's the kind of system we're working with. And that's the same with the zeros at the start. They're reminding us that the first column corresponds to x1 and the second one to x2, which is from before the problem, really, before the matrix is written. You know, I mean, anyway. I hope that answers your question. There are some ambiguities here, for sure. Like, given a system, which one's the first column, which corresponds to the second column, the third, right? Like, if you have variables, which one's the first? If I've got x, y, z, w, I say x, y, z, w, but some of you say, what? No, w, x, y, z. So w is the first one, x is the second one, y is the third one, z is the fourth one, right? But you're wrong, because x is the first one, y is the second one, z is the third one, and w is the fourth one, right? But, you know, that's just, anyway. All right, so let's look at some applied problems, if you guys don't mind. Now, the applications I'll start with here are pretty tame. Ooh. I think I spent too long talking about your homework and such. I better project some things here. Hope you can forgive me. But the applications, like there's just a few tricks for the application problems that we need to sort of get. Now, are you guys all electrical engineers? So there's like a couple of you. So that means the rest of them should have to learn circuit analysis, right? That's just fair, that we have circuit analysis on the test, right? Yeah. That's not really fair. So I won't do that. But there might be circuit analysis in the homework, right? Because in the homework you have this thing called a book, and you can talk to the electrical engineers amongst you, and they'll help you write down your equations, right? But there's some things that we can all understand. Somebody just do one of those by hand, and then I'll project. But what example am I on? 5. So check this out. Suppose you want all cubics whose graph contains let's say 1, 4 and minus 1, 6. All right, do 2 points fix a cubic? Definitely not, right? 2 points don't even fix a quadratic, right? So what is a cubic? What's it look like? We're talking about p of x is something like, you know, I'll use ABCD. ax cubed plus bx squared plus cx plus d, right? That's our model function. A, B, C, and D are parameters, okay? And if we want the graph to pass through those 2 points, what's that mean? It means that when we plug in the point into the model, it has to work, right? So this, we need what? 2 things. We need p of 1 is equal to 4, and we need p of minus 1 is equal to 6. What's that look like here? Well, that's A plus B plus C plus D equals to 4. And how about minus 1? Minus A plus B minus C plus D equal to 6. So it's tempting for me to do this problem even without a matrix technique. Like I can almost see the solution here without using the matrix technique. But let me use the matrix technique just to be, you know, careful. So we've got 1, 1, 1, 1, 4, and minus 1, 1, minus 1, 1, 6. So I can do row 2 plus row 1. And this is what? This is A, B, C, D columns, right? It's a linear equation in A, B, C, D. And so row 2 plus row 1, so I got myself a 1, 1, 1, 1, 4. And I've got myself a, excuse me, 0, 2, 0, 2, 10. Right? And, okay, so that is going to be giving me 1, 1, 1, 1, 4, and 0, 1, 0, 1, 5, which then gives me, subtracting row 2 from row 1, 1, 0, 1, 0, 0, 1, 0. Oh man, this is cool. Let's see here. So I was doing row 1 minus row 2, so that's minus 1, 5. We should check me on this, all right? Of course, you guys could use the MATLAB, right? Do you guys have MATLAB on your personal computer? If you're a math major and you don't because you took the Mathematica course, that's okay. But you can also get MATLAB, and it would make your life easier with regard to this course, I think. And I think the way to, how do you guys do that as students? You just go to the Wolfram website and put in your school email, and it does it. So you did the same way I did, except instead of saying you're an educator or instructor, whatever it was I claimed to be, you put in student and stuff. So, all right, let's see here. Come on. I always regret opening my computer to email with personal information. So let's not do that. All right, so on my website, one of the things that's super convenient for us. So here's your handy dandy course website, right? Come on. Right up at the top, with this, I think this is really, really good for you guys to use at the start of the course, especially. But this website will let us check our work really quick. We've got what? How many rows? 2 rows. How many columns? 1, 2, 3, 4, 5 columns. You guys know about rows and columns because you took an Excel course here, right? So I don't have to teach that. Is that part of Minecraft? I don't know. Maybe not. I'm excited about Minecraft. Minecraft means I don't have to teach coordinates and physics anymore. We've seen your old videos. You never taught it. Fine, fair enough. Oh, look. So, behold. I can do row reduction today. I only made one significant mistake at the start of class, right? So, and the fact of the matter is, guys, no matter how much you know, how deeply you understand everything here, you will make mistakes. That's why it's really important to check your answers in here in as much as you can. All right? Anyway, so what does this all mean? This tells me that hey, what? Ah, you're dead to me. That's close. Oh, well. This means that A is equal to minus 1 minus C, and this means that B is equal to 5 minus D. Notice that I just went ahead and skipped the middle step of writing the equations. Do you see what's going on here, guys? I'm writing minus C because it would be plus C in the original equation, but I move it to the other side to give me a minus. And here, it would be plus D if I just wrote down this equation directly, but I want it on the other side, so it gives me a minus. Altogether, then what's our solution? Well, we're looking at minus 1 minus C times x cubed plus parentheses 5 minus D x squared plus CX plus D such that C and D are real numbers. There you go. That would be the solution set in this case. That's the set of all cubic polynomials whose graph contains these 2 points. Yeah.
What happens if you move A and B over rather than C or D? Do you just make A or B all real numbers?
Then you'd get a different looking answer.
Okay.
But there are going to be 2 free parameters in the solution. Is this the only way to present it? No. But I just chose to present it in the way which is consistent with my standard solution. I would take the other thing you're talking about as a solution to this problem, because this doesn't have a standard solution, I would say. Like, this is open to interpretation, especially if I don't put this formula. Now, the way I could fix my grading would be to say, please use C and D to characterize your solution, right? I could save myself from grading. I need an unpleasant place, like
DMV.
DMV, grading DMV. Very good. Excellent. I like that. All right, so see if I can find our notes in here. Oh man. What we? Oh, that's right. I keep thinking we end at 9, which is not true. We still got 8 minutes. We're good. Right, because, okay, so like, guys, what just happened here is how all of these applied problems are pretty much done. Which is what? Come on. I don't want to look at it here. Well, sorry guys, I hate using the whatchamacallit here. I always have this thing open. Of course, now I don't have it open. Rats. So sorry. Don't worry, I'll make up for it by going overtime. You're welcome. All right, so I hope you're looking at these. If you're not, then where you been? All right, so this one is find a polynomial p of x. What I was going to say is, like, the way we solve all these applied problems pretty much is to use either just plug the data into the given model, which then gives us linear equations, which we know how to solve, right? Or there's some other ones where there's some sort of like more base physical principle which we have to go through in order to set up the equations, right? So if you're electrical engineers, that might be like Kirchhoff's voltage laws, Kirchhoff's current laws, right? Those give you a linear equation. If you're a chemist, we can look at like setting up, you know, chemical balancing equations. That gives us linear equations. There's also traffic flow problems for you. Is that civil engineering? What is that? Who cares about traffic flow? What's that? DMV? Oh, that's right. I don't know. These people in their traffic circles, don't get me started. But anyway, so here we're looking at a quadratic that goes through these 3 points. So you plug in the points, you get this lovely system of linear equations, and then I put it into the matrix. The ABC are decorative, obviously, right? And then I fed it to technology because I don't feel like row reducing something with ugly numbers like that, right? Let it be understood in here, once you get to an applied problem with like ugly decimals, you are free to use either MATLAB or the website. But the website's not so great because it will give you answers in terms of exact fractions, which are amusing, but not really what you want for this kind of problem, right? Anyway, so this one works out to just that. But it's the same thing we just did for this more complicated symbolic example, right? Same thing, just plug in the points, you get a linear system, you solve. And here's another one. This one is kind of like the one I just did in class, except this time I had what? 1, 2, 3 points for the cubic. What happened then? You get 3 pivot columns instead of just 2, which means since you have 4 variables, you just got 1 left over, 1 parameter in your solution. And that's why my solution's just in terms of that 1 variable c, right? And why did I use c? I think it's just because that's what appeared as like the, you know, the non-pivot variable. But you probably could use another letter, possibly. I don't know. I know you can use the non-pivotal variable to characterize a solution set. Whether or not you can use another variable, that's a question that concerns the problem. It could be that your problem necessarily has like a fixed to be 1, in which case I can't use a as the parameter. It just not, it won't work. It depends. So yeah. Here is yield traffic flow problem. We've got this silly traffic situation where you got 400 cars coming this way, 300 cars coming in that way, 100 cars leaving here, 600 cars going there, 100 cars going there, and then you've got an unknown number of cars going here, x3, 100 going that way, x2 going that way, and these are one-way roads, which is convenient for the analysis, because one-way roads means that you're only interested in positive solutions, right? If you assume that the pictured direction is the positive one. And so like the principle here is conservation of vehicles. Number of cars in equals number of cars out, right? None of the intersections are like a car manufacturing plant that are making cars and inserting them onto the road, right? We don't do that, okay? Same principle for circuits, like circuits. And then anyway, you get a linear system, and then what do you do? You slap it in a matrix, you do the row reduction, and we get this. So that tells me x3 is 0, x2 is 100, and x1 is 500. That's the solution to that problem. I think you got a problem like this in the homework. It might be slightly more interesting. Let's see here. This is actually the solution to lay 1.6 number 7. Did I assign that problem? No? Phew. All right. I'm not sure. I may have held off on the chemical. You guys have, I've forgotten which problems I've cut versus which ones I've kept in your homework. So like, did I keep the chemical balancing problem? You guys are like, I haven't done the homework yet. It's not due tomorrow. Why are you asking me, right? But that's not true. Some of you have been working on it. I saw. There are scouts among you, advanced scouts.
Distribution.
What's that?
Temperature distribution?
Temperature, oh yeah, the temperature distribution problem. The temperature distribution problem kind of tells you how to set up the equations in the problem before it, so you just kind of have to follow the problem setup. But so this one here is a circuit. You've got a voltage source, another voltage source, some resistors. I label some currents, I3, I1, maybe one of those is a 2. Oh, I2, I3, I1. I deal with physical currents, not mesh currents, you electrical engineers, you. So physical currents are actually conserved, and maybe mesh currents are too, I don't know. But anyway, so the sum of the currents going into a node is equal to the sum of the currents going out of the node. And you also have Ohm's law, which relates to voltage drops and such. But again, you'll get a system of linear equations in the currents and the voltages of the circuit, which then you can solve using, see this one I'm like, I'm not going to use a matrix. This is too simple. I'm just going to solve it by ad hoc techniques. And see, that's always a choice you can make, right? If the problem is sufficiently simple, do you really need the matrix stuff? For example, at the start of class, I was doing matrix techniques for 2x2 systems. That's slower than using the stuff I did day one, right? Adding equations and substitution is faster, way faster for my examples 1 and 2. My purpose in showing you that was just to show you that we can combine systems with the same coefficient matrix. But anyway, I think that's about all I got to say about applications. I'll let you guys explore more in the homework. And Monday, we're going on to matrices finally.